In this lecture, I will introduce you to the theory of linear regression. Linear regression is used for modeling quantitative dependency between variables. So, we examine if there's any dependency between a given response variable y and the predictor or explanatory variable or variables x. Linear regression can help answer the question if and how a change in x influences a change in y. And when I speak about linear regression, I'm just referring to models in which we have one y and one x. And when we have several x's, more than one x, then that is known as multiple linear regression, and essentially the same rationale applies on multiple linear regression as well. So what we are trying to do is to model changes in y or examine if and how changes happen in y as a function of x. So let us just look at this graph between sepal length on the x-axis and petal length on the y-axis. As you can see, they seem to be having a positive linear point scattering. The linear aspect of this scattering is very important, and that is one of the most important and fundamental conditions of carrying out a linear regression, that your x and y variables, they need to have a linear relationship between them. So the scatter plot between them should be linear, like so. And that is something we will cover in more detail in the subsequent lectures. But essentially, here is our x and y, and what linear regression will help us do is to explain the variation in petal length, which is the response variable on y, of versicolor species on the basis of sepal length, the predictor variable. So we will be able to explain if the variation in sepal length can influence petal length in a meaningful or a statistically significant way or not. So this is a simple linear regression equation, and it seeks to map the relation between response variable y and the predictor variable x on the basis of a linear model, and which is the equation of a straight line, y is equal to mx plus c. So essentially this is y, and we try to relate it to x by using the equation of straight line where a is the intercept and b is the slope. So yi is the response variable, and it is your ith response variable from your data set. So it can be just any y variable in your data set. A is the intercept, and this is the value of y when x is equal to 0. So this is in a way a baseline condition. B is the slope of regression, and this is very important, and this represents the change in y for every unit of x. So if our regression model does indicate that x does influence y, then B will tell us that what is the magnitude of that influence. And E, this is the error term. So this is the difference between the data point, or rather the response data point, and its predicted value. It is either known as a residual or the error term. So this is how the linear regression works. It tries to fit a best fitting straight line to describe the relationship between y and x. So this is y, this is x, and these are the data points, and it tries to fit in a straight line which it feels describes the relationship best. And so what you have over here are the actual or the observed values of y, and the values of y which fall on the fitted line are known as predicted values, because when we are trying to fit a straight line, the straight line, it can't wriggle its way through all these points. So the best it can do is to fit a line which is as close as possible to all the points. So what you don't see sitting on the line are your observed values, and what you have on the line is the predicted value, and by subtracting these you get the error or residual as we spoke before. So line fitting is done on the basis of ordinary least squares, and the upshot is that ordinary least squares, they rely on minimizing the sum of squared errors. So this is the error term, and we can square it. So we can square it for every point, and this is what I represents from 1 to n, that essentially all your points, they are going to have some error term associated with them. So we are going to square it, sum it up, and then minimize it. And this minimizing is done with the view of fitting the best line. The null hypothesis of linear regression is y is independent of x, or variation in y is not influenced by x. So more formally, the null hypothesis indicates that slope b is 0, so no quantitative dependency between y and x. And as I mentioned, multiple linear regression that involves one y and multiple x values. These are some formula. You don't have to remember these because you can just implement regression straight on in R, but it is just good to have some conceptual clarity, and I emphasize on that because linear regression and having a thorough conceptual clarity of what linear regression is, what it is telling you, what it is not telling you, interpreting the results, and so on, is the single most important step you can take in understanding more detailed and advanced analyses. And essentially, understanding of linear regression will underpin most of the predictive analyses you will encounter either in this course as we go on, or in your own life when you work with real data. So back to the lecture. In order to calculate the slope, we need these two variables where SSX is the sum of squares. Now xi is a standard notation and it alludes to a data point x. So this refers to the value of response variables from 1 to n. The value of predictor variables, x variables from 1 to n, and x dash on top. This represents the mean of that given predictor variable. And we subtract it, square it, sum of products. Again, the same notation applies. We subtract the values of x from the mean predictor value, y from the mean predictor y values, and that is the sum of products, and it measures the covariation between x and y. So we divide these and get the slope. Now, in order to evaluate the model, there are quite a few parameters out there, but the most common and the first parameter that you will quote in your study, and you see quoted in every statistical linear regression model studies, R square, whose value typically varies from 0 to 1, and this is used for evaluating model performance. We are advised to use adjusted R square in the case of multiple regression. So the closer is your R square to 1, better is your fit. So when you see a line like this, we can say that this is a good fit. And R square is a variable. Basically, it tells us the proportion of variation in y, the response variable that your model is explaining. So if your R square is say 90%, then we can say that the model explains 90% in variation in the value of y. So there's a very strong relationship between our response variable and the model that we have created. And if it's close to 0, then our fit is bad. So that's the first thing we do, is to look at the R square value and whether it is statistically significant or not. And for that we need the p to be less than 0.05. And now if we want to evaluate how useful the model is, then we will look at things like p-values of the slope and the intercept to get the final equation. And if the p-value of slope is less than 0.05, then we can say that the x variable, the predictor or the predictors, they have a significant effect on y, and then the value of the coefficient, it acquires some meaning. So we can say that, if there's going to be 1 unit change in x and it is a statistically significant slope, then the change in y will be the value of the slope. Now we will carry on and actually implement linear regression in R, and then carry on further with interpreting these results.